Now, let's talk about complex numbers. These often arise when we're solving quadratic equations. We'll begin with a simple equation, x squared equals -1. No real number satisfies this equation, so we will extend our number system with a new number that does. This number will be called I, also known as the imaginary unit, defined by the equality I squared equals -1. If you multiply I by a real number, you will get an imaginary number, such as 3i or 5i. From there, we can add together a real number and an imaginary number to get a complex number, such as 4 plus 3i. Here, 4 is called the real part of this complex number, and 3 is called the imaginary part. Note that every purely real number is considered a complex number. For example, the real number 6 can be expressed as 6 plus 0i in complex number form. Similar logic applies to imaginary numbers. We can visualize complex numbers in a two-dimensional plane, where the horizontal axis represents the real part and the vertical axis represents the imaginary part. This is called the complex plane. Note that the names here are rather poorly fitting. Despite the names real number and imaginary number, mathematicians don't actually consider either one to be more or less real than the other. In fact, the names were actually invented by a French mathematician called René Descartes, who genuinely hated the concept of imaginary numbers, not understanding how or why they would be useful, which they did turn out to be. Other names have been proposed, like lateral number by German mathematician Carl Friedrich Gauss, but imaginary number remains standard. As for complex number, the word complex just means having several parts in this context, namely a real part and an imaginary part. However, it may give the false impression of meaning complicated instead, which is not a useful idea to express in a name. Anyway, using complex numbers, we can now solve many quadratic equations that real numbers alone didn't allow us to solve. In fact, every solution to every quadratic equation is a complex number, possibly a real or imaginary number. Let's look at an example here. 3x squared plus 18x plus 75 equals 0. As a side note, when you go from the real numbers to the complex numbers, there are several contexts where it is conventional to use the variable z instead of x. However, x is often used in this specific case for some reason, so we'll keep using it. Anyway, firstly, notice the coefficient of 3 in the 3x squared term. Often it is more convenient to work with a coefficient of 1 on the x squared term instead. To do this, we can divide both sides of the equation by 3. We can distribute the division by 3 to each term, and the result will be x squared plus 6x plus 25 equals 0. You might end up with fractions when doing this, but luckily, the numbers end up working out nicely in this example. Now that we have x squared plus 6x plus 25 equals 0, let's do the same procedure from before. If we subtract the constant 25 from both sides here, we get x squared plus 6x equals -25. Now, draw a square with a side length of x. Then draw a rectangle with a width of 6 and a height of x. Cut the rectangle vertically in half and glue these two new rectangles to the sides of the square representing x squared. This forms a shape with a so-called area of -25, without taking that area literally. This shape is like a big square except for a missing gap, so we fill in the gap with a plug, which completes the square. The plug is a small square with side lengths of 3 and an area of 9, so we add 9 to both sides of x squared plus 6x equals -25, giving us x squared plus 6x plus 9 equals -16. The big square has side lengths of x plus 3, so we can rewrite this as x plus 3 squared equals -16. From this point, we can't use the same absolute value trick from before. Remember, that only works if we stay in the real numbers the whole time. Notably, it is straightforward to extend the absolute value to the complex numbers. The absolute value of a complex number is its distance from 0 in the complex plane, just like the absolute value of a real number is its distance from 0 on the real number line. This can be calculated using the Pythagorean theorem, but the specific details aren't that relevant right now. The main point is that an actual geometric distance only makes sense as a non-negative real number, so that is what the absolute value of a complex number must be. In the case of this equation, we can't just take the square root of both sides and get a non-negative real number on the right, so the absolute value method will fail. Still, we can split the equation into two cases based on the available possibilities. We know that the square root of positive 16 is 4, so what happens if we take the square of 4i? That's 4i times 4i, which can be rearranged to 4 squared times I squared. Then, 4 squared equals 16, and we can define I squared to be equal to negative 1. So this is 16 times negative 1, which is negative 16. But that's not where it ends. We can also take the square of negative 4i, giving us negative 4i times negative 4i, which is negative 4 squared times I squared. Negative 4 times itself is positive 16, and I squared is still negative 1, so we get negative 16 again. At this point, you might have noticed that while x equals I is a solution to the equation x squared equals negative 1, so is x equals negative I. This may raise the question: if we define I to be a number whose square is negative 1, but negative I is also a number whose square is negative 1, does that mean that the definition doesn't actually work? The answer is that we arbitrarily select the number I as a particular solution to x squared equals negative 1. It turns out that we could just as well have called the other one I, and we wouldn't be able to tell the difference when doing math. Tangent aside, let's return to the equation x plus 3 squared equals negative 16. We just found the two values that can be squared to get negative 16, so let's split our equation into two cases. X plus 3 equals 4i, and x plus 3 equals negative 4i. This can also be written as x plus 3 equals plus or minus 4i, for shorthand. Now to solve for x, we just need to subtract 3 from both sides. This gives us our final answer, x equals negative 3 plus or minus 4i. In other words, x equals negative 3 plus 4i, or x equals negative 3 minus 4i. These are the solutions of 3x squared plus 18x plus 75 equals 0. Checking these solutions will be left out of the video for the sake of time, and it is instead left as an exercise for the viewer. For now, we are done with this problem. To close things out, we'll present a derivation of the quadratic formula. This formula is usually presented without explanation to algebra beginners, and it probably just looks incredibly confusing and random. However, as always, figuring out why something is true in math goes a long way towards understanding it. It turns out that we can derive this formula by simply using completing the square in the general case, and this is the standard method of deriving the formula. As before, we'll use a visual representation to show this process. We have a general quadratic equation, ax squared plus bx plus c equals 0, assuming that a does not equal 0. Like before, we want the coefficient of x squared to be 1, so we'll start by dividing everything by a. This gives us x squared plus b over ax plus c over a equals 0. Now we'll subtract the constant term, c over a, from both sides. This gives us x squared plus b over ax equals negative c over a. Now we'll represent the left-hand side as an area, like before. For x squared, we draw a square with side length x. For b over ax, we draw a rectangle with height x and width b over a. We then vertically cut the rectangle in half. Each of the two resulting rectangles still has a height of x, and since the original width is b over a, dividing that by 2 gives us b over 2a. We glue one of the rectangles to the right of the square representing x squared. Then we rotate the other rectangle by a quarter turn and glue it to the bottom of the square. This shape almost looks like a square, but there is a missing gap in the bottom right. So we can fill in the gap with a smaller square to complete the larger square. The smaller square has a side of b over 2a. We can find its area by squaring that number, which gives us b over 2a squared. Using exponent properties, we can distribute the squaring. This gives us b squared over 2 squared a squared, which is just b squared over 4a squared. This value is what we should add to both sides of our equation from before, giving x squared plus b over ax plus b squared over 4a squared equals b squared over 4a squared minus c over a. Now that the left-hand side of the equation represents the area of the completed square, you can re-express it in terms of the square's side length. The side length is x plus b over 2a, so the area is quantity x plus b over 2a squared, which we can substitute on the left-hand side. From here, the rest of the process is basically just a bunch of algebra. The diagram probably won't be that helpful anymore, but each step of the solution will be clearly motivated. Remember, this is exactly the same as the previous times we've completed the square, just in the general case. Anyway, since we have something squared on the left-hand side, we should consider the principal square root of the right-hand side. It could be equal to x plus b over 2a, but it could also be equal to the negative of that same value. As you'll recall, squaring a number is the same as squaring the negative of the same number. So, that's why we need to take the plus or minus square root on the right-hand side in order to get rid of the squaring on the left-hand side. Now, we've almost solved for x. To isolate it, all we need to do is subtract b over 2a from both sides, and we're done. Well, almost. This is probably not the form that you're used to seeing the quadratic formula in. To fix that, let's first look inside of the square root. We want to combine the two fractions together, so they have to have a common denominator. To do this, take the fraction c over a, and multiply the top and bottom by 4a, giving us 4ac over 4a squared. Now we can combine the fractions to get b squared minus 4ac over 4a squared. We can distribute the square root to the top and bottom of the fraction. Taking a square root is the same as taking something to the power of 1/2, so we can use the same exponent properties from before. Square root of quantity 4a squared creates another sign ambiguity because it could be plus 2a or minus 2a. However, because we could have either a plus or a minus dividing a different plus or minus, that must give us just a single plus or minus. And using that covers all possibilities. Since we can pick either plus 2a or minus 2a, let's choose plus 2a for convenience. Finally, since both fractions already have a common denominator, we can combine them immediately. This gives us the typical form of the quadratic formula. X equals negative b plus or minus the square root of quantity b squared minus 4ac over 2a. And now, we're really done.